All right, we'll make do. Perfect. Thanks so much, everyone. So I need to clarify that this would probably just be numerical method because I kind of just figured this out last week and it takes a bit of time to sort it out. But anyways, with some motivations. So this application might seem completely abstract, but I'm looking to study the formation of lipid nanoparticles. These are used to deliver mRNA, so very familiar from COVID vaccines. The thing is that it's a multi-scale, multi-physics process. So essentially the process works by taking lipids like oil and combining it with, and you dissolve these lipids in ethanol, you take the mRNA, you put it in water, mix the two together very quickly, and you form these lipid nanoparticles that encapsulate the mRNA. So you have the fluid dynamics of the mixing, you have the phase, the precipitation of the particle, and then you have electromigration and different forms of interactions even at the particle and in intramolecular level. So very multi-scale, multi-physics process. Just some pictures of like different aspects of the process and the kind of particles that you form. The thing is that we don't fully know the structure of these LNPs, even though more than 4 or 5 billion people have been injected by them. And that's mildly concerning to say the least. So we hope to figure that out. And with that in mind, there's this class of models called the Cahn-Hilliard equation. I think there have been several presentations by very distinguished speakers. And the idea is that it comes from a very deep place of thermodynamics because we are introducing this parameter that describes the presence or absence of a substance. And it's a kind of a smooth interface. So we presume that the interface, we presume that the interface very smoothly. It's not a discontinuous system. And the evolution of this phase field variable is governed by the minimization of the free energy. So whenever you want to describe a new system, you write down the energy and then you take the variational derivative. And typically you would use the Allen-Cahn equation for non-conserved phase field variables, like whether or not it's crystalline or amorphous, and you use the Cahn-Hilliard equation for conserved phase field variables. So in this case, it would be concentration of volume fraction. So just kind of like a rough overview of how it works. We write on an energy expression. We write on an expression for the total energy. So there's a homogeneous energy called F and a gradient term. We take the variational derivative and we bash it through the conservative equation, either assuming that the transport is directly proportional to the chemical potential or of the flux. And now, here's the thing. Why are we so interested in logarithmic potentials? So the vast majority of the papers or in the literature actually kind of assumes a quartic polynomial, a double well shape. And that's cool for math papers, but it's not cool for physics because in reality, the logarithmic term, which is the entropic term right there, is deeply, it comes from first principles thermodynamics. And that's one thing I think has not been violated in the universe yet. So in that regard, the Flory-Huggins equation, which is given by 3, is really the foundational premise upon which we can do very complex thermodynamic work. And this is just kind of to show you a couple of examples. So Flory-Huggins, the excess energy is a very simple term. We can go to way more powerful models like activity coefficients or thermodynamic perturbation methods, but it all requires us to handle that logarithmic term. So with that in mind, let's just consider like a simple 1D implementation and with Neumann boundary conditions at the end. The gradient energy term kappa is, we can also derive a first principles expression for that. I'm happy to walk anyone through that if they're so interested. So pretty simple vanilla stuff, 1D. And this is the kind of simulation results. Okay, great. For small chi values, converge, no success. And if you can see, the time step requirement becomes a bit stiff. I mean, there is a bit of a stiffness element to it. And eventually, it just stops working altogether. And that point, that's actually a problem because we're not going to be able to do any meaningful simulations because for these lipid nanoparticle systems, we're going to get huge chi values because, as you can imagine, oil is not very soluble in water. And think of chi as how strong the interaction is between the two. With that in mind, so there are a couple of things that could go wrong in the solution with the logarithmic potential. The first is multiple timescales. So kind of just going back to the previous video, you can see that the early processes are very quick. You know, the sharp gradients quickly smooth out. But then after that, it becomes slow. And you can imagine, like with spinodal decomposition, it's going to take a long time. So you have multiple timescales in the process. But we can use adaptive time stepping for that. So and this has already been done in the literature, so nothing too complicated there. Non-linear, if we look at the structure of the equations, The Jacobian should be pretty nice. So I don't think that the nonlinearity should pose any particular issue. Then stiff, again, we talked about that. Implicit time stepping with maybe a IMEX scheme to handle the nonlinearities could be a possibility. But then the singularity, that seems to be where the problem is. And I kind of tried fighting with Phoenix for a while, but then I decided, okay, I want to understand the problem from scratch and in a way that I have access to every single thing. So I thought, okay, let's write a simple finite difference, a simple second order central difference finite difference solver, fairly standard stuff. And then when I was playing around with it, I realized we need to regularize the logarithm. What this means is that when chi is very large, the equilibrium compositions, which is the value that the phase field wants to go to, goes to like 10 to the minus 16 or 10 to the minus 17, and the system does not like this. So in the Newton step, that would essentially cause a log error to be like NumPy would return a log error, and that tells me we found the source of the mistake. And the trick that I did was that I just thought, hey, why not fit a cubic spline? Because splines are awesome. And it turns out splines actually work really well. And the thing is that if we define the spline, if we take the logarithm term and we define it from epsilon to 1 minus epsilon, and then map that back to a spline that is defined from 0 to 1, it's a bit of a dirty engineering trick, I agree. But if we keep epsilon sufficiently small, it's a reasonable approximation for all intents and purposes. And so, okay, with that trick in mind, I think I just want to quickly establish some key tests that can help test if things are working and if the simulation is correct. So the first thing is total mass is conserved, total energy decreases. I can't go above or below 0 and 1. And I can also track the interfacial tension, kind of see if that makes sense. So the interfacial tension is basically the energy between two phases. And it turns out it actually works pretty well. So we're able to simulate chi about 50, which is way more than what we're able to do with a naive implementation. And mass conservation is doing perfectly well. Energy is decreasing. There's no issue with the positivity property of the system. And we are able to get pretty reasonable estimates for the interfacial tension. Now, there's an interesting discussion about how the interfacial tension actually reaches a steady state value much quicker than the interface profile, but that's for another day. There's also an interesting discussion in the thermodynamics community on that property, but we can talk about that separately. So yeah, I mean, apparently, so seems like we've figured out something that could solve the problem. Now, next steps. So as I said, seems to work pretty well, but the thing is that there's a lot more testing I need to do to figure out, to see that it works properly. And I kind of need to really extend this to more efficient stepping schemes rather than just doing backward Euler. So see if I can get into a Crank-Nicholson or a BDF or try some IMEX scheme to make it a linear solve instead. We also need to move it to 2 or 3 dimensions because, again, these nanoparticles are forming in 3-dimensional systems, and they have like 5 components. So I need to handle all 5 components. And hopefully, when I figured all of this out in finite difference land, I'm going to parse it over into Phoenix because then I can run it on a cluster way more easily and also exploit all the beautiful features within Phoenix. With that, I would like to thank everyone for your time and happy to get anyone's feedback or insights on the use of a cubic spline. And also, I have a little GitHub repository where I put up examples for phase field models just for fun. Happy to talk more about that as well. Thank you.